Yeah, now in this video we'll see how to solve the same problem using superposition theorem. Okay, so the modality of this video is of course using superposition theorem. Okay, so what does the superposition theorem say? Superposition theorem says we consider only one independent source killing all other sources and finding out the branch current or node voltage that we require, and we repeat the same process. Okay, uh, and we repeat it n times if there are n number of independent sources. So in this problem there are two independent sources. This is 1 volt independent voltage source and this is 2 amp independent current source. So we do have two cases. Okay, so case 1 is we consider uh, let us say we consider only the 1 volt source and kill all others, and we have only the only other source that we have in this problem is 2 amp source. So if we consider the 1 volt source, we are now killing the 2 amp source. Okay, so how do we kill the current source? We simply open circuit this. So if I redraw this circuit, remember I am redrawing it only for case 1, that is I am considering only the 1 volt source. Okay, now if I redraw, so this is my 7 ohm resistor, this is 3 ohm, so this would be 7 ohm, 1 ohm, 3 ohm. Since this is open circuited, this branch is not present anymore, so this can be clearly be left out, and this is my 2 ohm resistor. Remember, my objective of the problem is to solve for the current that is flowing through this 7 ohm resistor using the superposition theorem. Okay, like previously, let me label them with the same names. So let this be A, let this be B, and let this be C. Okay, now this is a much simpler problem wherein we can see that 7 and 3 are in series because the same current flows through those two. So if I now redraw this circuit, so this is nothing but 1 volt voltage source. So here I have a 10 ohm source which is in parallel with 1 ohm source, and this is nothing but my 2 ohms resistor. So this is 10 and this is 1. Remember, I want the current flowing through the 7 ohm resistor, so that is nothing but the current through the 10 ohm resistor. So here I'll simply use the voltage division principle. I'll find the voltage across this 2 ohm resistor. So if I get the potential at this node, then I can use Ohm's law. This potential minus this potential divided by R would give me current through 10 ohm, which is of course current through 7 ohm. Okay, and this potential I also know from the problem, it is directly equal to 1 volt. Okay, so the total resistance or the current, the voltage drop across this 2 ohm resistor from the voltage division can be computed as, so this is nothing but C. So VC would be nothing but the voltage, the resistance value across which the voltage is required, that is 2 ohms, into the total voltage. Here the total voltage is 1 ohm and divided by the total resistance seen by the circuit. That is nothing but that 10, that is nothing but 10 and 1 are in parallel, and that equivalent is in series with 2 ohms. So that would give me something like this. The parallel value of 10 and 1 would give me 10 into 1 by 10 plus 1, which is nothing but 11. So I add it with 2, so I get a value like this. So if I plug in these values, what I get is 0.687 volts. Okay, 0.687 volts. Now I is nothing but so this potential, which happens to be 1 volt, minus this potential which I just now computed to be 0.687, and divided by resistance which happens to be 10 ohm. Remember, 7 and 3 are in series, So whatever current is flowing through the 3 ohm is flowing through 7 ohm and vice versa. So this is nothing but if I compute this, I get a value like 0.03113 amps. And remember, what is the direction of this current? See, if you see, it is going from A to B, isn't it? So this is going from A to B. Okay, now I'll start with case 2. So in case 2, I consider only the independent current source, that is I consider only the 2 amp source. Okay, and I kill the 1 volt source. Actually we have to kill all other sources, but all other sources in this case is nothing but 1 volt source. So here clearly kill 1 volt source. So if I redraw the circuit, killing the 1 volt source is nothing but replacing it with short circuit. So if I redraw the circuit, this is what I have. So this is 7, this is 1 ohm resistor, this is my 3 ohm resistor, 7 ohm, 1 ohm, 3 ohm. Remember, this is node A and this is node B and this is node C, and this is my 2 amp source in series with a 3 ohm resistor, and in this branch I have a 2 ohm resistor, and this is my 2 amp. Okay, because I have to kill the voltage source, I have to replace it with a short circuit. Okay, so if we look at this, we cannot actually comprehend. So what I'll do is I'll redraw this circuit in this manner. Okay, so this is 3 ohm. Okay, actually 7 ohm is between B and A, and B is at one end of 3 ohm, that is this one, and A, because of short circuit of the voltage source, A can now be treated as connected to ground. As you can see here, A, this node A is connected to ground. So I can draw something like this. So this 7 ohm can actually be drawn in this fashion. Okay, so of course this 2 amps current source is also there, which is in series with the 3 ohm resistor. Okay, and of course similarly the 1 amp is the 1 ohm resistor is connected between C and A. C is at the other end. See, this is B. C is at the other end of the 3 ohm resistor. Okay, so 1 ohms one end is connected to C, the other end of 1 ohm is connected to A, which happens to be this one, ground, because of short circuit. Okay, so this finishes my equivalent circuit. Okay, of course this is 1 ohm. Of course this 2 ohm resistance between C and the ground is also present, so that is this one. Okay, now if I redraw the circuit, okay, so this is what I have. Okay, so this is nothing but 7 ohm. Okay, this is 2 amps, which is in series with a 3 ohm resistor, and from this picture we can see that 2 and 1 are in parallel, and that parallel combination is in turn in series with 3 ohm. So 2 and 1 in parallel will give me 2 by 3 ohms. In series with resistor I add 2 by 3 with 3 plus 3, so what I get is nothing but 11 by 3, that is connected over here. So this is nothing but 11 by 3 ohms. So this is nothing but B, and because A is short circuited to ground, this becomes my A. Okay, now I'll apply simple KCL here, currents entering and currents leaving. Okay, so the entering current in that node is 2 amps, which should be equal to leaving current. The leaving current, this leaving current can be written as VB minus 0 by 7, and this leaving current can be written as VB minus 0 by 11 by 3. That is nothing but VB by 11 by 3. Okay, so if I rearrange everything and do some arithmetic, I will find out that VB is in fact 4.8125. So VB is in fact 4.8125. But remember, the object of my problem is to find out the current through 7 ohm. So the current through 7 ohm resistor is nothing but VB by 7. So which happens to be 4.8125 divided by 7. Okay, so this is nothing but 0.687. Remember the direction, it is going from B to A. Okay, that finishes my case 2. Okay, now in order to get the final answer, I have to sum up these two answers, that is sum up the current through the 7 ohm resistor from case 1 with the value that I obtained from case 2. If we see here, we got a value in the case 1, the current through 7 ohm resistor is 0.0313 and the direction is from A to B. But in the second case, the current is 0.687 and it is flowing from B to A. So in effect, the current now is nothing but 0.687, which is flowing from B to A. Now I have to, because I have to have the same direction, I'll say 0.0313. So this current is also now going from B to A. So I have modified this value 0.0313 flowing from A to B as minus 0.313 flowing from B to A. Okay, so this gives me a value like 0.6562 amps, which is of course equal to 656.2 milliamps. Remember, what is the direction? It is flowing from node B to node A. So in the problem, so this is actually the current direction from node B to node A, and its magnitude is 0.6562 milliamps. Okay, so modality may be anything, and we obtain the same answer. Okay, thank you.